All right, hey guys.
Hey guys.
We are back with chapter 7. Back at it again.
Yep.
Hey, I'm excited about this chapter though. As you can see from the slide there, it says chapter 7 is titled Trigonometry, and sometimes that's a scary term. Easy. We're starting out with some stuff that you've seen, I don't know how many
a lot
years
of times.
now.
Yeah,
for several years now.
7th grade.
Yeah, we've talked about it. I know I've talked about it with my students. It's come up a couple times already this year, even though we haven't formally addressed it. And now we're going to formally address it finally. So we're talking in this first section about the Pythagorean Theorem. And so here is the Pythagorean Theorem, and maybe you don't know it by name, but you know it by this, by the formula itself. And so the formula is a squared plus b squared equals c squared. And we just need to know what those apply to. So Pythagorean's theorem is only true in a right triangle. It only applies in a right triangle. So if we look at the parts of a right triangle, we got to remember the pieces of a right triangle. And so the two sides of a right triangle are called the legs, and it really doesn't matter which one's A, which one's B. You can flip-flop those. It really doesn't matter at all. Which one's shorter or longer, if they're the same, doesn't matter. Okay. The longest side of a right triangle, always the side opposite the 90, is called the hypotenuse. Okay, and that has to be the C in the formula. That's all that really matters in the formula, is that longest side is the C in the a squared plus b squared equals c squared. Okay, we got to remember some things here about squares and square roots and things like that as we're solving this. Reducing or simplifying radicals and so on, but we'll work on that as we progress here. So just to jog your memory here, if we have this yellow triangle that we're trying to solve for that x on the right hand side there, we would set this into Pythagorean's theorem, and again, it doesn't matter which one you put the x in and which one you put the 4 in. And so if we go 4 squared plus x squared is equal to 6 squared. Again, the important part is that the 6 is by itself, it's the c squared, and go through and solve that. And so first thing you would do is square each one of those that you can. And so we would have 16 plus x squared is equal to 36, and then subtract the 16 from both sides. I think there's an in-between step here. Subtract 16 from both sides, and so we're going to get x squared equals 20. Now here's what I was talking about. You got to remember how to simplify some of this. If you have to solve that equation for x all by itself, you need to take the square root of both sides. X is being squared. We do the opposite. So you take the square root. And so if you take the square root of both sides, we're going to get x is equal to radical 20. But inside radical 20, you can break that down with our factor tree and do 2 times 10, 2 times 5. Because there's 2 2's in there, you pull one of them out and leave the 5 by itself inside. So it simplifies, just like we talked about in the last chapter, simplifying ratios and so on. You have to simplify radicals to 2 radical 5.
We should be familiar with this because we did some of that with the geometric means.
We did
on the worksheet.
Yeah. You've been working with radicals a little bit here and so on. So you got to remember how to do that. All right.
Okay, so as we move over to the next slide, guys, we're going to have the area of an isosceles triangle. Now, this is a bit of a stretch because we're trying to focus in on Pythagorean's theorem, but in this textbook, when you guys do some of the math problems in class, you're going to see that they're going to have you go back, and once you figure out the missing side using Pythagorean's theorem, they're going to want you to go back in and find the area of these triangles. And so what you're going to do is first you've got to develop a plan. Well, we don't know h, which means the height. Okay, the base of the triangle is 30 across the bottom. Okay, and so to find the base and the height of any triangle, guys, you got to look for a right angle. Okay, and so that's the key. So where my right angle is it's 30 across there, and then h going up to the top. And so we don't know what h is, so we can use Pythagorean theorem because it's a right triangle. When you break those two triangles up, they become two right triangles there. One leg is 15, the other leg is h, and the hypotenuse of the triangle on the right is 18. So you can make up the equation of 15 squared plus h squared equals 18 squared. So 15 squared is considered A, h squared would be considered B, and 18 squared would be your C. So then all you got to do is square 15, square 18, move things around, and you get h squared equals 99. Okay, square root both sides, so undo squared, and we get 3 root 11. Remember, 99, guys, is basically just 9 times 11, and 9 is a perfect square, so you could square root the 3, take him out, and leaves an 11 on the inside. So now, you're not done yet, okay? So remember, they wanted us to find the area of the triangle, so you've got to go back and plug in what you know into the formula. Okay, so now I'm going to take that the height is 3 square root 11, and I'm going to plug that into A equals 1/2 BH, Okay, and so my height is 3 root 11, my base is 30, and then I got to take half of that. And so there's the formula right there. A equals 1/2 of 30 times 3 root 11. Now, if you can do this in your head, half of 30 is 15, and then remember, when you multiply radicals, remember, you got to go whole number to whole number, and then the radical is just going to tag along to the back because it's irrational. So when you multiply things out, 15 times 3 is 45, and then the root 11 just kind of tags onto the back. So it's kind of like speaking two different languages is what I usually say. The guy on the outside speaking English, the other guy speaking Chinese, so they can't really communicate with one another.
Yeah, and I was talking about with radicals, you treat them like variables. A radical is essentially like an x or whatever. If they are the same, then you can add them. If they're not, then you can't. Here we're multiplying things, and so just as Mr. Bedella said, we've got some whole numbers or integers out in front. Radicals, they don't multiply. They're different. So what we would like you to see is some shortcuts within the Pythagorean Theorem process. And so we would like you to understand that there are things called perfect Pythagorean triples. Okay? And what we mean by that is just triples, three numbers that work to where they come out evenly. So those last two examples we had radicals in them. They don't work out like that. They work out to perfect squares. And so there are just some common ones that happen a lot. And so the more familiar you are with those, this chapter, the things that we do in this chapter will just be so much easier. And so here's a table. Now don't take it all in at one time. Just let's break this apart a little bit. Okay? What we're really concerned about is the top row. Okay? The columns are just different examples, but the top row. So the most common shows up over and over and over again. The easiest one, smallest one that comes out to perfect numbers is 3, 4, 5. So we'll always say a 3, 4, 5 triangle. That's a right triangle with one side 3, the other side 4, the two legs, and the hypotenuse of 5. It works because 3 squared is 9, 4 squared is 16. Add those together, it's 25. 5 is the square root of 25. And so it's a perfect Pythagorean triple. Now, if you take any multiple of that, it's like if you doubled that triangle and made the sides 6, 8, and 10, that's where the second row comes from. So a 6, 8, 10 triangle is just double the size of a 3, 4, 5. So just like we talked about similar triangles in the last chapter, that's a similar triangle, just twice as big. Okay? Same thing, if you triple every one of those numbers, 9, 12, 15, that's a perfect Pythagorean triple as well. If you multiply them all by 4, multiply them all by 5, whatever, they all come out to perfect Pythagorean triples. These are just the common ones that you see. Okay? So if we jump to the next column and look at 5, 12, 13, okay, again, that's just a common perfect Pythagorean triple. You see that in a lot of triangles. 5 squared is 25, 12 squared is 144, add those together, it's 169, square root of that's 13. If you double all those, you get 10, 24, 26. You don't see that one a ton. 15, 36, 39 comes from tripling them. We don't really see those a ton. They might show up every once in a while, but 5, 12, 13 shows up all the time. Okay? Same thing with the other two. 8, 15, 17, that's just a common triple that shows up. Okay? 7, 24, 25, that's kind of a weird one when you draw that because the 24 and 25 are so close to each other. And then that third side is really short compared to those. But it does work. 49 plus, what is that, 576 is equal to 625, which is 25 squared. So all those are perfect Pythagorean triples. The top four, the top row there of 4, you really need to do your best to memorize those. Just have those down.
Yeah, and the other thing, the key thing that I want you guys to take away from what Mr. Scritchell was saying was he kept saying if you doubled all 3 or you tripled all 3, make sure you remember that if you double one, you've got to double the other 2 in order for this to work.
Yeah.
You cannot have a 3, 8, 10 and say it's a perfect Pythagorean triple because that's not correct. It's got to be all 3 have to be doubled.
Yeah.
So they always got to be able to go back to that root Pythagorean triple in order for it to be correct. So just be careful because they are going to try to mess with you sometimes and give you a 3, 8, 10 and you're going to say, ooh, I remember that. That's a Pythagorean 3, 4, 5. Well, that's not entirely true.
Yeah.
So be real careful there, guys.
Yep.
But yeah, 3, 4, 5, 5, 12, 13, I'd say those are the 2 that we're going to see the most.
Oh, yeah.
But the other 2 are important to you. They're going to come. Uh-oh. Okay.
Here we go.
So,
technical snafus. Actually, we had to fix this slide, so we took a break there.
yes. we're
Changed
back.
clothes and came back.
And switch places.
Yes, just to keep you guys on your toes.
That's right. So, converse of the Pythagorean theorem. The converse of the Pythagorean theorem says that if a squared plus b squared equals c squared, then we have a right triangle. Originally, it says if you have a right triangle, then you know that a squared plus b squared equals c squared. So we're just switching that the other direction. So it kind of looks like this. If a squared plus b squared equals c squared, then you have a right triangle.
Right.
And so from here, guys, we're able to make a few more deductions. And this is the idea of, we can come up with the idea of an acute triangle if c squared is less than a squared plus b squared. We know that that triangle will end up being an acute triangle. And if c squared is greater than a squared plus b squared, we can come up with the fact, or we can deduce that we're going to have an obtuse triangle out of that. I mean, it's really not that big of a deal. It's just, it happens this way. And if you were to test it, you would see that this is happening. If c squared is greater, then you get an obtuse triangle. If c squared is less, then you get an acute triangle.
Right. Yeah. And so not all of this is the converse. The converse is just really the first one. But if you plug into Pythagorean's theorem, c squared equals a squared plus b squared, and it works, then it is a 90-degree angle. It's a right angle. If it's less than it, then the angle is less than 90. If c squared is bigger than a squared plus b squared, then the angle is bigger than 90. It's an obtuse triangle. So, all right. Okay, so we're going to test this other example here and look at whether this triangle is right, acute, or obtuse. And so we're going to use the Pythagorean theorem, a squared plus b squared equals c squared, and plug in the three sides here. And again, the critical part is that you keep the longest one in c. And so if we plug in that 9 squared is 81, the 15 squared is 225. And then remember how to square the 3 radical 34. You square the 3, which is 9, and then that's out in front or being multiplied by the radical 34 squared. The radical and the square just cancel each other. The square root of something squared just goes away, and so it's just 34. So it's 9 times 34. And so if we add the 81 and the 225, that ends up equaling 306. If we multiply 9 times 34, that equals 306. And so from the last slide, because those two are equal to each other, it has to be a right triangle. Okay? So the test in Pythagorean's theorem showed that the two sides are equal, therefore it is a right triangle. Okay? That compared to this next example, the first part of this question is decide if these side lengths, is what it's referring to at the bottom there, can form a triangle, just a triangle, any kind of triangle. And so you got to remember back to chapter 4 where it says that any two sides of a triangle have to add up to more than the third side. And so we're looking at the side lengths here, and the side lengths are 10, 15, and 5 radical 3. So that 5 radical 3, we just need to get a feel for how long that is. Okay, and so the radical 3, the 3 is somewhere between 1 and 4, so the square root of it is somewhere between 1 and 2. So it's about 1.7, the square root of 3, and so when we multiply those two together, it's going to end up being about 8.5 or so. Okay, so we got 10, 15, and about 8.5 for that third side. So 15 is the long side, and so if we take the 8.5 and the 10, those do add up more than 15. And so, and the others do too. 10 plus 15 is more than 5 radical 3, and so on. It all works. No matter what two sides you add together, they always add up to more than the third side. So yes, this is a triangle. Now we need to do the same test we did up above, and so we're going to square each of these. And so since 15 is the longest side, that's the C, so we're going to take 15 squared and compare that to, so maybe a question mark here, as to, you know, is that equal to, greater than, less than? So 15 squared compared to 10 squared, and plus 5 radical 3 squared. Okay, so 15 squared is 225. How does that compare to 10 squared is 100? And remember how to square something like this. So you square the 5 is 25. Square the radical 3. Again, the radical goes away, and so you just get the 3. So 25 times 3 is 75. So on this side we have 100 plus 75, 175. Other side is 225, so the c squared is actually bigger than the a squared plus b squared. Therefore, the angle is bigger than 90 degrees. Therefore, this is an obtuse triangle. So the answer to that second part of the question is obtuse. Okay? All right, guys, that's Pythagorean's theorem and the converse of Pythagorean's theorem. Anything else there?
No, sir.
Okay. Good luck with the assignment here, and we'll see you in class.